Hello friends, I am Nkejan from Skill on Tech. Today I am presenting a video how to save energy in pump performance and control. Pump characteristics curve. You can see a picture where pump characteristics curve is shown. Head is at y-axis and flow is at x-axis. There are two curves are shown. One is a steep characteristics curve and this is a flat characteristics curve. So pump characteristics curve can be changed by changing the speed of rotation as flow is proportional to and head is proportional to n square and power is proportional to n cube. Starting or stopping pumps operated in a series or parallel for pumps with radial impellers. This may be a cause for changing the pump characteristics curve. Changing the impeller outside diameter, flow is proportional to D. So pump characteristics curve can be changed by changing the impeller dia. Installing or changing the setting of installed pre-swivel control equipment for axial flow propeller pumps, changing the blade pitch setting, blade angle. So characteristics curve will also change. The effect of these measures for changing the characteristics curve can only be predicted for non-cavitating operating pumps. System characteristics curve. You can see this is a system characteristics curve. The system characteristics curve plot the head H system required by the system as a function of the flow rate Q. In a pump, we know the pump deliver a fluid that can be a water also to a particular destination that may be a tank or a reservoir. The flow goes through a discharge pipeline. So the basic requirement is we have to lift the water up to a certain height or elevation where tank is situated. So that height, that head is called static component. And when the flow which goes through a discharge pipeline where it faces surface roughness of the pipeline or throttling through a discharge wall in the pump. So the fluid faces some resistance during flow in the discharge pipeline, that is called dynamic component. So here these two components are shown. This is a static component, the basic requirement of fluid lifted up to a height, and second one is a dynamic component which is faces during flow of the discharge pipeline. A system characteristics curve can be changed by changing the flow resistance, by changing throttling, installing an orifice or a bypass line, rebuilding the piping. So that dynamic component will change. Changing the static head component, different water level or tank pressure. That is a static component. Pump operating point. In this picture we can see this is a HQ curve and you can see this is a pump curve and this is a system curve. The operating point of a centrifugal pump, also called its duty point, is given by the intersection of the pump characteristics curve with a system head curve. So this is a pump characteristics curve, this is a system head curve, this is a intersection point and this is a operating point of the pump. The flow rate Q and the developed head are both determined by the intersection. To change the operating point, either the system curve or the pump curve must be changed. Factors affecting the pump performance. You can see a efficiency curve and a pump characteristics curve. So here this is a head, this is flow, and these are the efficiency curves and this is a pump characteristics curve. The centrifugal pumps are characterized by the relationship between the flow rate Q they produce and the pressure H at which the flow is delivered. Pump efficiency varies with flow and pressure and it is highest at one particular flow rate. The figure shows a typical vendor supplied head flow curve of a centrifugal pump. So you can see the efficiency are changing with respect to head and flow. If you will require this head, then you will get this flow at this point. So efficiency, you can see this is increasing. If you will add, so the optimization of head and flow is must to achieve highest efficiency at operating point. The figure shows a typical vendor supplied head flow curve for a centrifugal pump. Pump head flow curve are typically given for clear water. The choice of a pump for a given application depends largely on how the pump head flow characteristics match the requirement of the system downstream of the pump. So we must understand the pump efficiency curves and operating point of the pump to optimize the pump performance. Effect of oversizing the pump. As mentioned earlier, pressure losses to be overcome by the pump are function of flow. The system characteristics are also quantified in the form of head flow curves. If we will change the head and flow, the system curve will decide the operating point of the pump. The system curve is basically a plot of system resistance that is had to be overcome by the pump versus various flow rates. Here you can see in this picture, these two curves are shown, characteristics curve, and two system head curves are shown. The system curve changes with the physical configuration of the system. The system curve depends upon height or elevation, diameter and length of piping, number and type of fittings, and pressure drops across various equipments in the discharge pipeline. A pump is selected based on how well the pump curve and system head flow curve match. The pump operating point is identified as the point where the system curve crosses the pump curve when they are superimposed on each other. So here, as we discussed, this system head curve and this pump characteristics curve are intersecting here at the point A, and this is the operating point if the flow is 500 meter cube and head is 50 meter. In the system under consideration, water has to be first lifted to a height. This represents the static head as shown here. Then we make a system curve considering the friction and pressure drops in the system. This is shown as the green curve. Suppose we have estimated our operating condition as 500 meter cube per hour flow and 50 meter head. So this is our head requirement and this is our flow requirement. So we can see that this system curve is intersecting the pump characteristics curve at point A here. And that is the best efficiency point where we are getting 82% efficiency. But in actual operation, we find that 300 meter cube per hour flow is sufficient for our requirement. So what we will do? We will throttle the discharge valve. The reduction in flow rate has to be effected by throttle valve. In other words, we are introducing an artificial resistance in the system by throttling a discharge valve. So due to this additional resistance, the frictional part of the system curve increases and thus the new system curve will appear and it will shift to the left. This is shown as a red curve. Here you can see this one. So the pump has to overcome additional pressure in order to deliver the reduced flow. Now the new system curve will intersect the pump curve at point B here. The revised parameter are 300 meter cube per hour at 70 meter head. The red double arrow line shows the additional pressure drop due to throttling. This one. This is an additional pressure drop. You may note the best efficiency point has shifted from 82% to 77%. We want is to actually operate at point C, which is 300 meter cube per hour on the original system curve. The head required at this point is only 42 meter. What we now need is a new pump which will operate with its best efficiency point at sea. But there are other simpler options rather than replacing the pump. If we need a new pump, we will purchase a new pump. It will be very costly and uneconomical solution. So what we can do, the speed of the pump can be reduced, or the existing impeller can be trimmed, or new lower size impeller. The blue pump curve represents either of these options. Efficient pumping system operation. To understand a pumping system, one must realize that all of its components are interdependent. When examining or designing a pump system, the process demands must first be established and most energy efficiency solutions introduced. Does the flow rate have to be regulated continuously or in steps? Can on-off batch pumping be used? What are the flow rates needed and how are they distributed in time? The first step to achieve energy efficiency in pumping system is to target the end use. A plant water balance would establish usage pattern and highlight areas where water consumption can be reduced or optimized. So we must know our water requirements and how it can be optimized. Good water conservation measures alone may eliminate the need for some pumps. Once flow requirements are optimized, the pumping system can be analyzed for energy conservation opportunities, means matching the pump to requirements by adopting proper flow control strategies. Potential opportunities for energy saving. So let us see the symptoms of your pumps operation. Throttle valve control system. It means your pump discharge valve is throttled. You have a lesser requirement of flow. So what may be the likely reason? Oversized pump. What are the best solutions? Trim impeller, a smaller impeller, variable speed drive, 2-speed drive or lower RPM. These are the solutions to save energy in case of you are throttling a valve, discharge valve of the pump. Bypass line partially or completely open means your pump is giving excess flow and that you are sending through a bypass line. It means it is an oversized pump. So what are the solutions? Trim impeller, a smaller impeller, variable speed drive, 2-speed drive, and you can reduce RPM also. Multiple parallel pump system with same number of pumps always operating means you are having a continuous requirement of particular flow and your all pumps are running always in a parallel. As we know, always same flow requirement may not exist. There may be flow requirement may be vary during the different times. So what may be the likely reason? Pump use not monitored or controlled. Solution: install proper controls. Constant pump operation in a batch environment means you are operating pump in a batches, means it is a wrong system design. You have to introduce on off controls to solve this problem and to save energy. High maintenance cost means your seals and bearing failures are occurring very frequently. Likely reason is pump operated far away from BEP, best efficiency point. That's why your maintenance cost is increasing. So what is the solution? Match pump capacity with system requirement. These are the potential opportunities for energy saving in pump operation. In the next part of video, I will give you some examples. So we'll see in detail how it can be done. Please see the part 2 of video. Thanks for watching the video. If you like this video, hit like button below. Share it with your friends and colleagues. Subscribe our channel for getting updates on upcoming videos. Please leave any comments, feedback to improve the videos. Thank you.